So, yesterday we saw the plan of the proof of Roth's theorem from the point of view of Croot and Sisask. So, today we carry out the full details of the proof and hopefully complete the proof of Roth's theorem from this point of view. There are many different presentations of Roth's theorem in the literature. I have chosen one which is particularly suited to the presentation of Green's theorem on three-term A.P.s and dense sets of the primes, which I will do next. So I have chosen this particular proof, and also because this proof, this method contains the germ of the ideas of Croot and Sisask, which they developed further into a very important piece of work in connection with Roth's theorem, and the best results on Roth's theorem known today come from these works. So that was the reason we chose this method. So at any rate, we of course have limited ourselves to proving only the weak version of Roth's theorem, which was stated several times. So I'll just state it only briefly. Theorem Roth weak version. And that is limit n tends to infinity Rn by n is 0. So this is the version that we are going to prove, and here Rn, as I've mentioned several times before, is the cardinality of any of the maximal subsets of the integers from 1 to n that does not have a non-trivial three-term arithmetic progression. Okay, so what is the first step of the proof? Step 1 is to let n be a sufficiently large integer, and let a contained in 1 to n be a maximal subset not containing non-trivial three-term A.P.s. Okay, then cardinality of A is Rn. This is of course the definition of R capital N. And next we define, so through this proof we will write, we set f to be the characteristic function of A. The reason for choosing f is because in the next part, when we do Green's theorem, is f, we will not necessarily use a characteristic function but a weighted characteristic function. So just to conform to what I'll do next, I use f here. Then the number of three-term arithmetic progressions, which is lambda f, which is some f of x, f of y, z, x plus z equal 2y, x, y, z in z. This counts, so lambda f is the total number of three-term arithmetic progressions in A, and we have seen that this has a Fourier expression, which is given by f hat t f hat t the square f hat t the square f hat of minus 2t dt, where f hat t is sigma fn e to the minus 2 pi I n t. Okay, at this point, I mean, in order not to annoy my thesis advisor who is sitting there, I will use the standard notation for this that analytic number theories use. So I will write E n t with a minus to denote e to the 2 pi I n t. Yes, to keep my Guruji happy. So therefore the Fourier transform, which is defined in this fashion. Okay. So next we said what was the strategy we wanted to adopt? That was to find. So we wish to find a finitely supported positive valued function g from z to r plus. So positive valued function on z such that one lambda f is close to lambda g, and two is that the support of g in cardinality is bigger than theta times the cardinality of A, where theta is some fixed number greater than 1. The main point is that theta should be strictly bigger than 1. Once you get such a thing, of course you have to say precisely what this closeness means, but once you get such a thing, then the support of G will contain be bigger than the cardinality of A, so it will contain a non-trivial 3-term A.P.s, because the cardinality of A is Rn, and anything bigger than that will contain non-trivial 3-term A.P.s, and by the Bernoulli's theorem it will contain several of them. On the other hand, if lambda f is close to lambda g, and since lambda f f this is the characteristic function of A, and A contains only trivial 3-term A.P.s, lambda g has to contain few 3-term A.P.s, and this is a contradiction. So you play these two facts against each other and you conclude Roth's theorem from this argument. So now this lambda f being close to lambda g in view of this Fourier formula here, so lambda f equal this Fourier formula. So in view of star, we replace 1 with 3, which is f hat is close to g hat. Okay. So now I must still tell you what this close to means. I'll do that in a moment after I review the choice of G that we made yesterday. So the choice of G was made in the following fashion. In order to first have some function which in Fourier transform is close to a given function, a convenient choice is to take the given function and convolve it with a function h. So because Fourier transform behaves nicely with respect to convolution, it's easy to compare f convolution h, the Fourier transform with f, with the Fourier transform of f. Secondly, f hat is close to g hat forces on us that f hat 0 must be close to g hat 0. But f hat 0 is sigma f of n, and g hat 0 is sigma g of n. And we, rather than close to, we look for equality of, so we'd like our g to satisfy sigma g of n is the same as sigma f of n. And to do that, the best choice for h, the simplest choice for h, is the normalized characteristic function of some set, of a finite set. So to meet these requirements, the simplest choice is to take h to be equal to 1 by cardinality of b times the characteristic function of a set b, which has to be fixed. Now the question is, how do you make the support of this, how do you choose h or this b so that the support of g widens dramatically? Okay, you want the support to be large so that you can play the, you can use the argument that I outlined before. And we saw yesterday that if you were to so since sigma f of n is the same as sigma g of n by assumption, but you still want the support of g to be much bigger than the support of f, that would mean, and since f takes value up to 1, you would want g to take much smaller values so that its support grows. Okay, so you would want g to be strictly, gn to be strictly less than 1. And since it's a finite support, that means that it is actually, less than 1, as in, yeah. So now, how does one choose the b? If you put in the definition, you see that your g of n is equal to the sum of the characteristic function of a, which is f of m, f of n minus m, let's say, into the characteristic function of b, m, 1 by the cardinality of b. And f is the characteristic function of a. So if you want this thing to be always strictly less than 1, then you need that, since these terms here are either 1 or 0, you need that no translate of b is contained in a. So you have to choose a b such that no translate of b is contained in a. In fact, this is going to be equal to 1, this sum divided by cardinality b is going to be equal to 1 exactly when the translate by n. So if g of n is 1, it means that the translate by n of the set b is contained inside the set A. Okay? Therefore, if you want this to be strictly less than 1, you need that no translate of b is contained in A. So the question was, what sort of sets should we choose? And the answer was, A is defined to be a set which doesn't contain 3-term APs, and if you want a set no translate of which is contained in A, then you just choose B to be a 3-term AP, because any translate of a 3-term AP is a 3-term AP, and you want that A should not contain a translate, and A by definition doesn't contain 3-term APs. So the right choice for B is simply a 3-term AP. Okay, so we chose then B to be equal to we then chose B, so we choose, or let's say we set here, we set B to be equal to 0, B, 2B, where B is to be chosen. B is still to be chosen. Nevertheless, once you take B to be, the capital B to be of this form, then you see that f of f of g of n is equal to 1/3 of sigma of f of n plus f of n minus b plus f of n minus 2b. And therefore, hence g of n, when it's not 0, g of n takes only two values, 1/3 or 2/3 when n is in the support of g. In particular, it takes values less than or equal to 2/3. What does this mean? This means that if you look at the size of the support, it's going to be 3/2 times the cardinality of E. So now you see from this that 2/3 times the support of G, I mean the cardinality of the support of G is greater than sigma G of n, because each G value is less than or equal to 2/3. And therefore, this is greater than or equal to say, this being equal by choice to sigma f of n, and this being equal to cardinality of A, we see that hence the support of G has cardinality which is 3/2 times the cardinality of A, which is huge. And if we choose B so that the G approximates is close to F in Fourier transform, then lambda has not changed much, but the support has changed dramatically. And this is something this is a contradictory situation which will lead to the only resolution of which is Roth's theorem. Okay, so that's the way. So now the question becomes how to choose B. Okay, but before coming to how to choose B, let me quantify this meaning of closeness. So I give you a simple inequality. Okay, it will take a few lines and an application of Holder's inequality to derive this inequality. I'll give you a precise inequality which will relate the closeness of, which will tell you lambda f minus lambda g in terms of the difference, L infinity difference between the Fourier transforms of f and g. Okay, so first so let me write down this inequality which I will prove. So I'll write this inequality in somewhat more general terms than is needed for just Roth's theorem, because the general version is exactly what we will use in Green's theorem. Okay, so I'll call this, these were some steps, review of steps from yesterday, and now I'll break this review to go to section 2. So for today, which I will call configuration control. Okay, this terminology is not mine. It comes from a paper of Browning and Prendeville. Browning and Prendeville, 2016, IMRN is the journal. So they had Roth theorem for squares, and this terminology comes from their paper. Okay, this together with another paper of Prendeville, so this is S. Prendeville and T.D. Browning. So together with another paper of S. Prendeville, this is 2017 Journal of Online Journal of Analytic Combinatorics. Combinatorics, 2017. these two I mean, I used them extensively in preparing these lectures. So you would benefit by looking up these together with a well-known paper of Helfgott and the Roth. This is in IMRN, I think something like 2015 or so. I don't remember the exact date. So these three papers I used a lot along with the paper of Kroot and Sisask that I mentioned earlier. So I'm using terminology from here, and let me state this as a proposition. Suppose that for some p satisfying 2 less than equal to p less than 3, we have let's say f hat, the LP norm of f hat is less than n to the power of 1 minus 1 by p, and the LP norm of g hat less than n to the 1 minus 1 by p. Then, so this proposition I will continue here. Then lambda f minus lambda g is less than or equal to the L infinity norm of f hat minus g hat divided by n to the power of 3 minus p times n squared. Okay, so this is the L infinity norm of the Fourier transform, difference of the Fourier transforms, and you see that this count. So lambda f was the count for the total number of 3-term APs weighted with f. Okay, the count weighted with f, and we know that the count is of order n square, and this tells you, this inequality tells you that if f hat and g hat differ by a small amount only, because this, again, f hat and g hat are of order n. So this numerator is of order, let's say, some epsilon times n or eta times n. Then this ratio is of order eta, and eta to the power 3 minus p is what you will save over the total count. So that will give you the difference between the two counts. Okay, so if you make these two as close as eta times n, then you will save eta to the power 3 minus p, provided you have these two bounds here for LP, and this here there are implied constants, and you have these. These are the bounds which, for the corresponding functions that we will look at, the Fourier transforms of characteristic functions of sets of primes, these bounds are called restriction theorems. Okay, when you actually get such a bound, this is called a restriction theorem, and this a key tool that will be used to prove this is being covered by Satadal using the large sieve. Okay, so that's where traditional analytic number theoretic tools come into this topic. It's in proving these sort of bounds in when we take up the prime case. In our case, these bounds for p equal to 2 is completely trivial. They just follow from Plancherel theorem. Okay, so we have seen. So we will use for Roth's theorem only the case p equal to 2 of this observation. So let me just write the consequence before I get into the proof. So I just write it in a different color. So in our case, f is the characteristic function of A, and hence you see that f hat the L2 norm of this dt, which is the L2 norm of f hat, is the same as the L2 norm of f, which works out, I mean, okay, this is not the L2, it's the 1 squared, but okay, the square of the L2 norm, which will work out to be equal to cardinality of A, and therefore is less than or equal to n. That is for f. Okay, but for G also you have a similar thing, simply because G is easily related to f using its definition. So G is equal to f convolution. So, oops. Yeah. So G being equal to f convolution 1 B by cardinality of B, and we have G hat T is f hat T times 1/3 of 1 plus E bt plus E 2 bt. Okay, so you have this, and therefore I should have continued to write in orange color. Therefore, G hat T is less than or equal to f hat T, because each of these three things is bounded by 1, and so you get that G hat T is less than or equal to f hat T, and therefore the L2 norm of G hat T also, so you have integral whole square is also less than or equal to n. Okay, so you see that f and G satisfy the hypothesis that is there here for p equal to 2. So in our case, in Roth's theorem, we take p equal 2. Okay, if f were supported in primes, then you will not get these bounds for, no, you will get the same bound, except that it would not be valid for p equal to 2. That is what the restriction theorem would give. It would give it between p is 2 and 3. And then you, therefore, in Green's theorem, you will choose a p which is between 2 and 3. But since the saving depends on 3 minus p, the bigger, so the closer p is to 2, the better the saving. So you just choose, say, 2.5, just simply to get a bound, and that's what you do. So there you have to choose p necessarily between 2 and 3. And I mean, there it's a non-trivial thing to establish such a result. Here it's trivial, because we are looking at subsets of 1 to n which are dense. So these observations are trivial for p equal to 2. Okay, so there's a big difference in this respect between Roth's theorem and. So okay, therefore we have to prove this particular inequality, which is actually a very simple application of Holder. For p equal to 2, it's just Cauchy-Schwarz. For other p, since I want it generally, it's an application of Holder's inequality. So let me just do it nevertheless for the sake of the people learning these things for the first time. So lambda f is in its Fourier expression, it is f hat t squared times f hat of minus 2t dt, which it's better to think of as simply integral 0 to 1 f hat t times f hat t times f hat minus 2t dt. So what I'm going to say will work as well if you replace these f's by f1, f2, f3, as long as the fi's satisfy those conditions given there. Okay, as long as the fi satisfy those bounds, you may as well, you don't have to consider the same function here. You can have f1, f2, f3. So you have to compare this integral with the one for lambda g, which is integral 0 to 1 g hat t, g hat t, g hat of minus 2t dt. Okay. So to make a comparison between two trilinear expressions, you know that the standard thing is to use the relation a1, a2, a3 minus b1, b2, b3 is equal to, let me say, a1 minus a2 times b2, b3, or rather a1 minus b1 times b2, b3, a2 minus b2 times a1, a3 plus a3 minus b3 times a1, a2. Right? You just write down where AIs and BIs, so you can, we have this where AI, BI are in C. Any complex numbers, whatever it's whatever the elementary identity that you get, you just check because there's some telescopes into what is given. Now you will apply it here, and when you apply it here, you're going to get three terms like this. The first one will read f hat minus g hat, then f hat times, g hat times g hat of 2t, okay, minus 2t. This will read similarly f hat minus g hat, f hat times g hat of minus 2t, and similarly here. So the structure of each of these terms is similar. There is one term which will have an f, the difference in Fourier transform, and then there are two other terms which will either be f hat or g hat minus 2 t or g hat t, f hat minus 2t or f hat t. So each of these three terms is very similar in structure. And this 2t is not important, it's just under change of variable, it would just disappear. So all these functions satisfy those bounds, and since this is the difference of two functions who satisfy those bounds, this also satisfies that bound that is written there. Something is not cancelled? Ah, yeah, you're right that the last one here must be B3. The last one must be B3. Then it cancels? Yeah. Pardon? A1, A2? A1, B2? Did I make another mistake? Okay. No, I think this is correct. This works. This should work. See, it would work cyclically. You just replace, the point is I've written it like this. You should have a product of the AIs, then a AI minus BI, AJs, J less than I, a product there, then a AI minus BI, and then the product of B J's, J greater than I. This is typically the structure of a term, except that I've put the AI minus BI's in front, so this is correct. Okay? It's Okay, thanks for pointing that thing. So fine. Therefore, the structure of each of these three terms is the same. So I may as well consider, in order to estimate these three terms, I may as well consider uh, um, integral. So we may consider estimating integral phi 1, phi 2, phi 3 in absolute value dt, okay, 0, 1, whatever. I'll just for brevity write integral phi 1, phi 2, phi 3, where the phi i's all satisfy phi I, the LP norm is less than n to the 1 minus 1 by p. So once one has the right estimate for this, you can plug it in for each of these three terms, and up to a constant you will get what is stated in the theorem. So now how does one estimate this? Here you just first split phi 1 and apply Holder's inequality. So you have mod phi 1, phi 2, phi 3 is equal to, let's say, I'll just write it anyway like this, phi 2, phi 3. This 1 here I split as this to the power of 3 minus p, phi 1 to the power of p minus 2, and then phi 2 and phi 3. Okay, taking use of the fact that p is between 2 and 3. And now in the integral, I remove this this part alone as an L infinity bound. So I take phi 1 L infinity 3 minus p, and then I have phi 1 to the power of p minus 2, phi 2, phi 3. Okay, and now I apply Holder's inequality here with the three exponents. So I have this here. So I note that 1 by, now note that 1 by p by p minus 2 plus 1 by p plus 1 by p is equal to 1, because you get p minus 2 plus 2 by p, which is 1, right? So you apply Holder's inequality to estimate this integral with these three exponents, okay? And if you apply Holder's inequality to estimate this integral with these three exponents, you will end up with I'll write it here perhaps. You will end up with integral phi 1, phi 2, phi 3 is less than or equal to the L infinity norm of phi 1, 3 minus p, and there you will get phi 1 to the power the LP norm to the power of p minus 2, phi 2 the LP norm, and phi 3 the LP norm. Okay, because this particular exponent here has a p minus 2 in the denominator and a p below. So when you raise it to p minus 2 power, you get this thing here. Okay, and now you have bounds for each of these. So this is less than n to the power of 1 minus 1 by p. This is also less than n to the 1 minus 1 by p. So you have totally n to the 1 minus 1 by p times. So this is going to be less than or equal to phi 1 L infinity 3 minus p times n to the 1 minus 1 by p to the power of p, which is going to give you n to the p minus 1. So now if you put in that p minus 1 into this expression, you finally get which hence integral phi1, phi2, phi3 is less than or equal to p1 L infinity 3 minus p, and here n to the power of p minus 2, and you write this n to the power p minus 2, this you write as say n to the power of 3 minus p minus 3 times n square, and put the p minus 3 below, so you will end up with L infinity norm here by n to the power of 3 minus p times n square. Okay, so you get this bound. Now, phi 1, right? Now I have, of course, chosen these expressions such that phi 1 is always the difference in the Fourier transform, okay? Because phi 1 is always the difference term in the way I have written these three terms and therefore this is going to always read f hat minus g hat or f hat 2t minus g hat 2t. The 2 doesn't matter, and you will up to a constant simply get this expression that's given here. Okay? Any no problem? What is the incompatibility? N to the p minus, no, one moment, n to the p, you get n to the p minus 1, okay, yeah, that is correct. This is just that I was careless to write it like this. It is n to the p minus 3 times n square. Okay, so it's n to the p minus 1, which I write as n to the p minus 3 times n square, then divide the n, and this is the bound. Okay, so you see that these so number of solutions to x plus y equal x plus z equal 2y, so weighted by f or weighted by g, is controlled in fact by the distance between the Fourier transforms in L infinity times the n square factor, which is the one that you would expect, which is the order of the number of solutions. Okay, so you can write down this inequality slightly more generally, not necessarily for the equation x plus z equal 2y, but for any translation invariant equation or any such equation in any number of variables, and that is what is done in the reference I mentioned, Browning and Prendeville. If you look up their section, and they'll give you the same thing written out more generally. Good. So this is tells us what the precise meaning of close is in terms of Fourier transform, and now we must get to trying to make a choice of b, little b, so that f hat is actually close to g hat. So that's the last thing on the agenda. Once we do that, we are in a position to complete. So the next thing is 4, which is choosing. So, or rather I would say here, since I keep using choosing, let's say fixing b such that L infinity f hat minus g hat is small. So that's the objective here. Okay, so it's good to write down the expressions for so g hat, g being equal to f convolution 1b by b, b is 0, b 2b, and therefore g hat t is equal to f hat t times 1/3 of 1 plus e bt plus e 2 bt. So you have this, hence g hat minus f hat t is less than or equal to f hat t. Okay, it's equal to f hat t times here 1 by 3 1 minus e bt plus 1 minus e 2 bt. Right? Simply by subtraction, therefore you have that L infinity norm of g hat. So let's not go there. So g hat t minus f hat t is less than or equal to f hat t minus here this difference, as I told you, you have the classical inequality which tells you that this is less than 2 pi times the distance on t, and this is less than equal to 2 pi times 2b t, but then by the triangle inequality for this distance you can write that as less than or equal to 4 pi. Which one? Here this is plus. Okay, so this is less than 4 pi times this expression bt and 2 pi divided by 3. So you get finally that thus g hat t is less than 2 pi times 2 pi times f hat t times bt. Okay, and we know that f hat t, we also know that the Fourier transform of f is less than or equal to n, because it's less than or equal to sigma fn, and f is a characteristic function of a, so it's less than or equal to n. So we want to make these two close, so we fix, let eta be between 0 and 1. We will fix it precisely in terms of n a little later, but let eta be this, and we will be happy to gain to choose b so that we make these closer than their trivial bounds. Okay, we know that this is also the case, and so is g hat t. Okay, we know that these two inequalities are true, and what we want to get is just a little less than less by a factor eta on this trivial bound for the two Fourier transforms. Therefore, if so, it makes sense to consider the set. So let S say be the set on which the Fourier transform f at t is bigger than eta n. So this is the set of all t such that f at t is bigger than eta of n. Okay. because G hat T just by the trivial estimate. You apply the triangle inequality, it's less than F hat T and it's less than N. So I can write here that this is less than F hat T is less than N. Okay. So now let us consider this set on which F hat T is bigger than eta N. First, if T doesn't belong to this set, then F hat T is less than eta N, okay, and then you just bound this trivially by less than or equal to half and you get a pi times eta N. So for T's not belonging to this set, there is no issue at all. You have already gained by a pi times eta on N, okay. The problem is to gain for the places where the Fourier transform is big, okay, bigger than eta N. And there, so if I have a B such that for all T in this S, so suppose there is a B such that B T is say less than epsilon, which is yet another small quantity like eta, which we will choose at the end. So suppose this is B is such that this is true for all T in S, okay. Then assuming that epsilon is also small enough, then you see for F on S, you can estimate F hat T trivially as N and BT will give you an epsilon and you have again saved an epsilon N. I mean, you've got epsilon N as the difference. So you will always gain, okay, provided you are able to find a B such that BT is less than epsilon for all T in S, and we will also require a size condition on B because for later purposes, so we will add the condition that the size of B is less than epsilon N. Okay, so suppose there is such a B, then we are done. Then we are done. We just choose such a B. So we are to prove that there is indeed such a B. That will be chosen, I mean, that will be required later because you see the support of G will shift from A by an amount to B, okay, because it's the convolution, so it will move the support. So in principle, the support of G can go and lie outside the interval 1 to N, okay. You would want to say that even if it does that, the intersection with the interval 1 to N is large. In that case, you would want to say that the size of B is not too big. Okay, so that's the reason why you need the size of B to be restricted. So this is the sort of thing that we require, and this is exactly the same thing that Professor Desier mentioned yesterday is what is called the set of such B which satisfy these conditions is called a Bohr set associated to S. Okay, and one would like to say that the Bohr set associated to this set S is non-empty. That is what one would like to say, provided of course you have chosen epsilon and eta. So for a particular choice of epsilon, eta and n, you would want to conclude that the Bohr set associated to S is non-empty, and then you choose a B from that Bohr set, and then you have Roth theorem by you take the 3-term arithmetic progression coming from that B, convolve F with that normalized characteristic function of that arithmetic progression, and that gives you, go through this procedure and you get Roth's theorem. Okay. So the idea is to convolve by a Bohr set, by the characteristic function of a Bohr set, and that principle we will see again when we come to Green's theorem, where again we will convolve by the characteristic function of a Bohr set in order to transfer from the situation in primes to the situation in the integers where we will apply then Roth's theorem. So that's the sort of thing. So now one has to look at showing that a Bohr set is not empty. Okay, this is a standard thing in elementary Diophantine approximation. Nevertheless, again, one of those things that need perhaps to be done at least once. So I will do this. So here now I come to 5. So yeah, non-empty 4, 6. Yeah, I'll go the whole hog and give you the full details because they are Bohr sets. That was a joke. Yes. Okay, so let us see it like this. Suppose, so what I want to show is a proposition. Again, one will need to use this restriction sort of the restriction bound. So I will again write this generally. So suppose that the LP norm of f hat is less than or equal to n to the 1 minus 1 by p for some p greater than 2. Here I don't need that p is less than 3. Then okay, let S be the set on which f hat t, so it's the t such that f hat t is bigger than say eta of n, that is S. Then if B S E is equal to n and z such that n is less than epsilon n and n t is less than epsilon for all t in S, we have that. So I'll write the conclusion here. The cardinality of B as epsilon is bigger than 1 by eps. So 1 by epsilon, or rather epsilon to the power of minus 1 by eta to the power of p plus 1 up to some constant times n. Or p plus 1 times n. So for so you need that this epsilon is, suppose that 0 less than epsilon less than half, 0 less than eta less than 1. Okay, there are like 35 seconds left, so I think I'll stop here and prove this theorem in the beginning tomorrow. Is that one needs to do this. Okay, thanks.